Hi everyone, in today's lesson we're going to talk more about related rates. So let's just do a couple of examples together. Example 1. The radius of a spherical balloon is increasing at a rate of 3 feet per minute. How fast is the volume increasing when the radius is 2 feet? So these problems are a little bit different than those latter problems that we did yesterday. So let's pull out some key facts. They want to know how fast is the volume increasing. So when I'm talking about an increase or a decrease in the shape over time, that's the rate or the derivative. So the how fast is dv over dt. How fast is the volume changing over time? So that piece of information will help us because that's our variable. Now the next piece, they tell us when the radius is 2 feet. Well, if the radius is 2, then we're going to have r being a variable of 2 feet. And then they tell us that the radius of the spherical balloon is increasing at this rate. So the rate is 3 feet per minute. So the radius, dr dt, the change in the radius over time, dr dt, is increasing at a rate of 3 feet per minute. So that's positive 3 because it's increasing. So since they want to know how fast the volume is increasing, we have to use the volume of a sphere formula. So that formula is volume equals 4/3 pi r cubed. And don't worry about memorizing this formula. If I ever give you a question like this, I will have to give you the formulas. So volume is 4/3 pi r cubed. So in order to find dv dt, we're going to have to take the derivative implicitly of all of the pieces. So the derivative of v is just 1, or the derivative of x is just 1. And we have to multiply it by dv dt. And then when I'm taking the derivative of 4/3 pi r to the third, this is just a constant in front. So you can think of it as something similar to, say I wanted to take the derivative of 5r to the third. You would still multiply the 3 by the 5 in front and get 15, and then drop down the power by 2. So the concept is going to be the same here. We're going to take the 3 and multiply it by the 4/3. The 3's will cancel, and we'll be left with 4 pi, pi is a number, r, and then raised to the second power. And since I took a derivative of r, we have to put dr dt next to it. So we can go ahead and plug in what we know. We know dr dt is 3 and the radius is 2. So we want to solve for dv dt. So the derivative of the volume with respect to time is 4 times pi. The radius is 2 and dr dt is 3. So to solve for dv dt, we're just going to multiply. So 4 times 2 times 3, and then tack on the pi. So 4 times 2 is 8, 8 times 3 is 24. So 24 pi feet cubed per minute. Reason why I'm putting feet cubed is we're talking about volume. Volume is in terms of cubic feet. Now you can multiply 24 times pi and actually get the correct answer or more simplified answer to the nearest 10th or 100th, but the question didn't specify. So it's fine to leave it just like that. Okay, let's try the second example. Okay, so in the second example, it says an oil spill from a tanker spreads out in a circular pattern, centered at the tanker's position. If the perimeter of the spill is moving outward at 2 meters per second, find the rate of increase of the contaminated area when the radius is 500 meters. So basically what's happening is, pretend like this is your truck. Here's my awful photo of the truck. And the oil is spilling out of this truck onto the floor. And it's making a circular pattern. So the best way I can show is like such. So say I have the oil, and what it's doing is it starts like small, then it gets bigger and bigger and bigger and bigger and bigger in this circular fashion. So you can see clearly the area of this space was getting bigger, as well as the circumference, the outside area. So those are the two formulas that we're probably going to need to use. So I'll just show you that one more time for those that need to see it. If we're starting with the oil tanker, this is how the first droplet would happen, then more, then more. Notice the circumference is increasing. Notice the area is increasing as this spill is increasing. So let's highlight some important information. They're telling you that the perimeter of the spill is moving outward at a rate of 2 meters per second. Perimeter is a fancy word for saying circumference. So the circumference formula that we probably should know is 2 pi r. And we know from this information that the perimeter or circumference is changing at a rate, derivative, of 2 meters per second. So my dc dt, the change in circumference over time, is 2. Then they say they want you to find the rate of increase. So find the rate, that means derivative, right? Find the rate of increase of the contaminated area. So they want you to find dA dt, the derivative of the area with respect to the time. They want you to find that when, lastly, when the radius is 500. So when r is 500. So the rate of the increase in the area means, this part, means that we're going to have dA dt, right? This dA dt piece. So we're going to have to take the derivative of the area formula. So let's do that. So I'm going to use this blue now. So if area now of a circle is pi r squared, we're going to take the area of each, the derivative of each of the pieces. So the derivative of A is 1 times dA dt. And the derivative of pi r squared is similar to before. Take the 2, drop it in front. So 2 pi r. And then I took the derivative of the radius with respect to time. So if I want to find dA dt, sorry I keep changing from capital to lowercase, but dA dt, that's what I want to find when my radius is 500. So the only thing left that I would need to answer this question is dr dt. What is the radius changing over time when the radius is 500? So that's where we're going to use this formula. So this is kind of like a double formula. We're going to have to use the information from formula number 1 to help us with formula number 2. So let's take the derivative of this first equation. So the derivative dc dt, you could put 1 times it, but we don't need to. And the derivative of 2 pi r is just 2 pi. But then we took the derivative of r with respect to time. So we can go ahead and plug in my dc dt as 2. We can plug in my radius, or excuse me, we can just leave the dr dt at this point, and we can solve this equation for dr dt. So all we'll have to do is divide both sides by 2 pi. The 2's will cancel. So the dr dt, sorry for squishing it, is just 1 over pi. That's what I'm getting from here, 1 over pi. So we can go ahead and put that right in here, 1 over pi. That's my dr dt. So it's actually nice, this top pi and bottom pi will cancel. So my dA dt is just going to be 2 times 500, which is 1,000. So 1,000, now we're talking about area, so 1,000 meters squared per minute. Or sorry, seconds. Sorry, the last example was in minutes. So meters squared, because we're talking about area, per second. All right, I know this one's a little bit harder, but this one requires 2 formulas, where the first one did not. We'll practice more of this tomorrow, so if you have any questions, now's the time to jot them down. And if not, I'll see you in class tomorrow. Have a good night.